Hello, men, and we're ready for another session of Physics Coach YouTube. Last week we were looking at uniform circular motion, otherwise known as UCM. First thing we did was we looked at a car going around a circular track, of course with friction. And we also looked at roller coasters in the normal force. We looked at a roller coaster going, or a car, going into a dip, and going over a dip, and becoming weightless. And then today we're going to do some cars going around a track that is banked, and we're also going to look at a couple other interesting things. So if you remember last week, we had a car going around a circular track of a certain radius, and the car had a velocity tangential to the track. And what we saw when we draw the free body diagram looking from ground level, we saw that the weight of the car, mg, and the normal force, Fn, were there as usual, but for circular motion, we need to have some radial force. And this would be our free body diagram. However, there's really no such thing as a radial force by itself. So what we have to do is replace that with some other real force. In this case, it would be static friction. Remember, it has to be static friction even though the car is rolling, or even though the car is moving. It's got to have static friction, otherwise the car would be sliding with kinetic friction. So static friction it is. But today we're going to do a different kind of track. This is going to be a banked track. So the track would look the same as this track from above, but looking at it from the side, we would see that the track was banked, and on both sides of the track, so the car could go around in a circle, somewhat like some of the race tracks like Daytona in Florida, which is banked at approximately 33 degrees, I think it is, which is pretty steep. So to do this problem, let's just look at one part of the banked track, and we'll draw that in. This is different from an object sliding down a hill. If we have an object sliding down a hill with or without friction, it will accelerate in that direction, obviously. But if you're driving a race car, you don't want to slide down the track. You want to stay at the same level. So for example, if these are the two sides of the track, you would want your car to be at this same level as it goes around the banked turns. So we have to do this problem a little bit differently. So back to the single side of the bank track. So we have a car here like this, and here it goes around the track away from us. The real forces free body diagram for this, move this guy over, would look like this. So we'd have the weight of the car down, and we would have the normal force perpendicular to the track. But what we're going to find here is that the normal force has to be larger than mg. And at first that sounds kind of wrong, because we said when we were on an inclined plane it had to be smaller than mg. The reason it slid down the bank was that the normal force wasn't large enough to keep it there. If we increase the normal force to the proper amount, what we're going to find out is, if we complete this little parallelogram here, we find out that the sum of these two forces would be horizontal. And this then would be the radial force. So what's the difference here? Why is Fn larger? Well, if this is a 90-degree angle and this is a 90-degree angle, Fn here is a hypotenuse. So it has to be larger than any of the other sides. For example, Fn must be larger than mg. If we do an inclined plane, what we find out is that mg is smaller than mg is larger than Fn, and because of that, when we complete our parallelogram, what we find out is the acceleration is, or the force down the hill is mg sine theta, and this is the normal force. Now, if you look at the diagram, in this case, you find out that mg is the hypotenuse, so therefore mg is greater than Fn. Because mg is bigger than Fn is not large enough to support that object, and it has to slide downhill. With our banked track, it's the opposite. The normal force is larger than mg, and it's able to keep that mass on the same level. Okay, so let's redraw that diagram over here so we have our own copy of it. So down here, you would have mg. Up here, we would have the larger F normal. And that's it for now. That's the real forces diagram. So where's the radial acceleration going to point? It's going to go horizontal, not down the hill. Let's do the modified diagram now. So this is going to be mg. And we need the y component in the upward direction to equal mg. Bring him down a little bit. It can be equal to mg. It's not Fn. What is it? If we look over on the real forces diagram, we're looking at this red thing here. If this is the angle of the hill, which you may not understand why, but we'll get to that later, this red thing would be Fn over here, Fn times the cosine of theta. So let me get that out of there because it doesn't belong. So over here, we would call this thing Fn cosine theta. Again, remember, we're not in the first quadrant here, so it's going to be cosine rather than sine. Then we have another component over here on our real forces diagram. It would be this blue one in the x direction, and that, of course, is going to be this one. That's going to be Fn sine theta. So this circle diagram is our modified diagram, and that's the one we can play with. Okay, so how are we going to do this? This will be a little bit different. First, let's look at the x direction. Some of the forces in the x direction would be equal to ma in the x direction, but that's actually the radial direction. So let's change those to show that the x direction is really the radial direction in this problem. So what do we get there? We get Fn sine theta. But let me back off on that a bit. So what we get here is that F radial is equal to m v squared over r. As I said earlier, there is really no F radial. That F radial is really Fn sine theta. So we replace this with Fn sine theta equals m v squared over r. That's as far as we can go because we don't have a value for Fn. So where are we going to get that value for Fn? Well, in the other direction. So let's take a look at the y direction. Some of the forces in the y direction would be equal to ma in the y direction. And of course, you don't want the car to accelerate up or down, so this acceleration would go to 0. What's left then is Fn cosine theta minus mg equals 0. Now we're going to do something here. Get over there. That I don't know if we did this before or not, but what I'm going to do is move the mg over to the other side. And now we have two equations that look similar in one way. It's Fn on both sides times some trig function equaling something else on the other side. So we're going to do a little move here that Again, I'm not sure if we did this before or not. We're going to divide this sine equation by the cosine equation. Can you do that? Yes. I'm not going to justify that right now, but we will look at that. So Fn sine theta equals mv squared over r. And we're going to divide that by Fn cosine theta equals mg. Now, you may wonder, can you do that? Yes. Let's say we had 3 plus 3 equals 6, and 5 plus 7 equals 12. We add up the right side here, you see that we get 18. We add up the left side, we also get 18. And if we divide 6 by 12 over here, I should say 6 by 12, not add them up. So 6 divided by 12 will give us 1/2. And over here, 6 divided by 12 will also give us 1/2. So yes, any two things that are equal to each other can be divided by any two other things that are equal to each other. If you didn't follow that, it's okay. It works. Okay, so what do we get when we divide this by this? The FN's cancel. We get tangent of theta equals the m's cancel, b squared over gr. And as we've done before, we're going to solve it for b squared. B squared equals gr tan theta. And that's it. That's the equation for the banked track. What does that mean? Let's say that we have a large banked turn, and we want to find out what speed we can go around that turn given its radius and its angle. So let's say we have g, of course, 9.8 meters per squared. Let's say the radius of the track is 100 meters. Let's say the angle of the track is, of the turn is, let's say, 15 degrees. So it'd be the tangent of 15 degrees. So let's run that through on our calculator. So your calculator, of course, should be out as soon as you see a number. Let's take a look at that calculation. Oops, I forgot something. We have to take the square root of that thing. And what we get there is v equals 16.2 meters per second, which is very roughly 32 miles per hour. Now let's crank the angle of the track up to, let's say, 30 degrees, which you're approaching the angle of the Daytona Raceway. Now, of course, the radius of its turn is possibly larger than that. That's a pretty big turn, though. I think that's about the size of Daytona. I'm not sure. So now we're going to substitute in here 30 degrees, and we'll see what we come up with when we get V30 as opposed to V at 15 degrees. So we'll get your calculator and punch this in, and we find out that we can go around this banked turn at about 23.8 meters per second, which is not twice as much as you might expect. It doesn't work that way, and neither do square roots. This is more like about almost 50 miles an hour as opposed to before 32. What else could you do with this equation? Well, you can solve for anything you want if you know what speed you want to go and what the angle of the track is going to be, then you could solve for the radius. Or if you move the radius, you could solve for the angle, and so on. So that's the bank track problem. I want to go back and examine one other little thing there that we were talking about earlier. So let's take a look at that next. You might remember a while ago I said that this angle up here is equal to the angle of the hill. How does that work? Well, what we have here are two parallel lines. And these two angles, of course, from geometry, are equal. Then we have a right angle here, or a right angle here, or a right angle there. So if we look at our large triangle, we have theta and a right angle. And if we look at, let's say, our top triangle, the top angle, this angle in here would also have to be theta because we have a right angle on that triangle. So if we have a triangle with two triangles with a right angle in them, and they also have another angle in common, this pink one here and this pink one here, then therefore the third angle, the green theta, has to be equal also. Actually, I should have had this right angle in here to be more correct. Okay, so if you followed that, good. If not, it still works. Okay, so let's take a look at another problem, and that would be the rotor ride. I think they have ones now, the new ones are called graviton or something like that, but the old rotor worked like this. You had a floor which was above the bottom of this cylinder, and you would have your passenger up here, and there he would be on the wall, and you look at this, it's like a penguin. Okay, so all right, so we have a penguin up here, and he's standing on the wall. Doesn't look like on the floor. Doesn't quite look like it, so cheat a little bit there. All right, so what we're going to do then is we're going to turn the rotor on, and we're going to make it spin, counterclockwise from above. And as we get up to the correct speed, what's going to happen is the floor is going to drop out, and the rotor, and the penguin, I should say, will be suspended on the wall in some physics way. So the floor now is down at the bottom of the rotor, and the astounded penguin is on the wall. Okay, so what's going on here? Well, first we'll start with the free body diagram, of course. And we have mg down. And you might wonder what keeps the penguin up there. Well, we had a problem the other day where we had a box against the wall, and we pushed in on the box. And the reason the box didn't slide down was that there was a static friction force holding it up against its weight trying to pull it down. The other thing that happened was when we put this applied force onto the block, we got a normal force back out from the wall. So that problem of the box trying to slide down the wall is a setup for this problem of the penguin being suspended on the wall. So let's get rid of that and do the penguin and the rotor problem. So this force here that keeps him from sliding down the wall is static friction. And this force that's coming out here is the normal force. And you might say, wait a minute, why is there nothing over here? Well, this is uniform circular motion. Oh, we get out of here. This is uniform circular motion, and for uniform circular motion to go in a circle, you don't need two forces canceling each other out. In fact, you can't have two forces canceling each other out, or the thing won't work. So let's take a look at the equation. Net force in the radial direction equals NA radial. What is the radial force? Well, it says right there, it's Fn. And what is MA radial? MV squared over R. Well, that's about as far as we can go on that one. We don't know Fn, so let's go try the y direction. Some of the forces in the y direction would be NA in the y direction. And what do we have up? F static. What do we have down? Minus mg. And we know that there is no acceleration in the y direction. So this side will be 0. Let's have static. Static, as usual, is mu static Fn minus mg equals 0. I'm going to move this mg over to the other side. because we're going to pull that little trick that we did earlier. We're going to take this equation here and divide it by this equation over here. What we're going to get then is going to be Fn equals mv squared over r. And we're going to then cancel out the Fn's. We cancel out the mg's or the m's. And what we're going to get is that mu static is equal to g r over v squared. If I do that right, and that looks good. Now usually we solve for v squared, so let's just do a little flip here of the v squared equals gr over v static. Now you might remember the bank, not the bank term, the flat term, said something like v squared equals mu static gr. The rotor says gr over mu static, so this would be the rotor equation. Say, why is it different? Well, one was flat on the ground, this one is flat on the wall. Obviously, something's got to be different. If we had a higher coefficient of friction on the flat track, the car would be able to go faster. If we had a higher coefficient of friction on the rotor, what would happen? So if mu static gets smaller, larger, I should say, then v doesn't have to be as fast. So that means if you have the wall on the rotor and you have your penguin up here on the wall, if you have very high friction, in fact, it was high enough he could stick on the wall, but that would be a pretty high coefficient. So if you had a higher friction, you wouldn't need to spin the rotor as fast. If you had a lower friction, you'd have to spin it much faster. In fact, if there was no friction here, then you would have to spin him at an infinite speed to get him to stick to the wall, because there's no way he'd be able to do that just as a nice flat-backed penguin. Another thing, what if r gets larger? Well, if r gets larger, then v must be higher. So if you're going to make a rotor, you don't want to make a really big rotor with smooth walls. You want to make a low radius rotor with high coefficient of friction. And that's what you see in the amusement park rides. The wall is fairly rough and the radius is fairly small. Therefore, you don't have to worry about your penguin slipping down the wall. You may remember the movie 2001: Space Odyssey. They had a rotating platform out there, a big wheel, and there was 4 spokes on it. And in one scene, there was a guy standing down here on the wall, looking at a guy standing up here on the wall, who their heads were pointing toward each other. Why? Because as this thing spun around at the correct speed for its radius, there was an artificial gravitational force here. It's not really gravitational force, it's a radial force, an F radial. But that made them feel like that F radial was a normal force, and that's what you feel as your weight. If you didn't follow that last thing, that's okay. But the key thing here is, for now, until I can get back and talk to you in person, that this is how you derive that equation. It's a little tricky, just like the last one was a little tricky, but what you need to do here is, if you don't understand how these things work, go back, look at this video again, take notes on it, ask somebody questions, ask me questions, send me an email, whatever you need to do. That's it. So I think that's enough problems for today. We're in this about 25 minutes. So If you're finished, you can work on something else or talk to other people about this. Obviously somebody, maybe the proctor could replay some of the video if you want to do that, or you could just look at it on your own computer. Obviously you would need earphones on that, so everybody's going to be in a different place. They get all confusing. Okay, so we'll see you guys pretty soon, and have fun with uniform circular motion. This will be, by the way, in chapter 5, over on the right-hand column, along with the uniform circular motion for the cars on the flat track and the roller coasters from last week.